In this video, we'll take a look at a few more derivative rules and then a lot of derivative examples. So the last big general derivative rule that we're going to talk about for right now is the sum and difference rule. And it says if you have two differentiable functions, then if you take the derivative of f of x plus or minus g of x, the derivative is simply f prime of x plus or minus g prime of x. Essentially what this piece here is saying is it's saying that the derivative will, quote, distribute over addition and subtraction. So this is really nice. The way I sort of describe it is that the derivative kind of in quotes, air quotes, plays nice with addition and subtraction, meaning that addition and subtraction are really not going to give you a big problem. It's not going to change the process of taking the derivative dramatically. It sort of acts in a way that you would sort of expect or want it to behave. So if I wanted to take the derivative of f of t equals 5t to the fourth minus 7t squared plus 6t plus 10, I'm basically just going to take the derivative of each one of these terms, work my way down the line, and add and subtract the results together. So f prime of t, I'm going to start by looking at, okay, what's the derivative of 5t to the fourth? Well, I'll use my power rule, multiply by my power. I'll have 20t subtract 1. I should have to the third power now. What's the derivative of negative 7t squared? Well, I multiply by my power. I should have negative 14t to the first power. And there we go, that's it. Derivative of 6t. Be careful with this one. This is really 6t to the first power, so when I take its derivative, it'll look like plus 6t to the 0, but we don't often write t to the 0 because t to the 0 is really just 1. So I'm just going to leave it as plus 6. If you want to write t to the 0, that's fine too. And then what's the derivative of 10? Well, 10 is a constant. The derivative of any constant is just 0, so that term drops off. So here is my derivative. So really not a huge earth-shattering rule. It sort of works in the way that you would like it to and a way that you would expect it to. One more quick example here. G prime of x is equal to, so let's see, derivative of x cubed. So I multiply by my power, 3x, subtract 1 from my power, 3x squared. Derivative of negative 6x squared, well, that's going to be minus 12x to the first power. Derivative of negative x, here I'm going to multiply, this is really negative x to the first, remember. So I'll have negative 1x to the 0th power, or just negative 1. And derivative of 4, I know that's just a constant, so derivative of 4 is 0. Here is my derivative, g prime of x. So this is a really, really nice rule, and I should say, when we say the derivative will kind of distribute over addition and subtraction, this is not always the case, as we'll see later on in this section. It turns out that multiplication and division are actually going to give us a bit of a hard time here. So we kind of have to enjoy this while it lasts. So let's see, what else should we talk about? We should talk about exponentials. So first of all, this guy right here, f of x equals e to the x. Remember, this is an exponential function where e is approximately equal to 2.71, and then I forget the rest, to be honest. But it's an irrational number, kind of just like similar to pi is, right? It's an infinitely long decimal. That decimal does not repeat, it does not end. So e is kind of this, it's a really interesting number that pops up in a lot of interesting places. But one of the reasons why it's so interesting is if you're working with the function f of x equals e to the x, that function is differentiable everywhere, meaning the derivative exists everywhere, and the derivative of e to the x is just e to the x. So that's kind of really cool, I think. It's a function that is its own derivative. When I take the derivative of e to the x, I get back e to the x. So we're going to work with that in this example. Here I have f of x equals, f of x equals 2x minus e to the x over 2. And actually, I'm going to rewrite this. I know most of us don't prefer to have fractions, and I think it might be a little bit difficult to worry about that e to the x in the numerator. I can pull that apart and say 2x minus 1/2 e to the x, and I think that's going to be a lot easier for us to work with going forward. Part A, though, says write the equation of the tangent line to the graph of f of x at x equals 0. So, okay, I want the equation of the tangent line. We're going to, like I said, we're going to see this all the time here. If I want the equation of the tangent line, I need the slope of the tangent line, which means I need the derivative. I need f prime of x. So let's go ahead and take the derivative. Derivative of 2x, that'll just be 2, minus here. Now I got to take the derivative of this guy. Remember we said earlier in the last video, our constant multiple rule says our constant multiple doesn't really have a dramatic impact. We just bring that constant multiple down and we multiply it by the derivative of e to the x. Well, the derivative of e to the x we said is just e to the x. So I should have just e to the x. And here is my derivative. So that's the first part of my problem, is I need to go and I need to find the derivative so that I can find the slope of the tangent line. Once I have that, I need to do, let's see, two other things, right? I want an equation of a tangent line, so I need an x value. I'm given an x value right here, so that's good. I need a y value, and I need a slope. Let's work with the slope because we just found the derivative, so let's just go ahead and use it. Remember the slope of the tangent line is given by the derivative. So I'm going to take the x value that was given to me, and I'm going to plug that into my derivative and see what we get. So f prime of 0 is equal to 2 minus 1/2 e to the 0 power. So we're just going to simplify this. 2 minus 1/2, let's see, e to the 0. I know anything finite to the 0th power is just 1. So I have 2 minus 1/2 would be 1.5 or 3/2. I prefer fractions, so we're going to say that's 3/2. This is our slope. So I have my x value, I have my y value, or excuse me, I have my x value, I have my slope. I need my y value, right? That's what I'm looking for, is I don't actually know what my y value is right here. Well, if I want to work with my y value, I want to go back to this original function f of x, either this rewritten form that we have right here or just the original form. Either one should be fine as long as we have rewritten it correctly. So to find the y value, I'm going to take this x value of 0 and I'm going to plug that in. So f of 0 is equal to 2 times 0 minus 1/2 e to the 0 power. And I'm just simplifying this as much as I possibly can. 2 times 0, that gives me 0, minus 1/2, we just said e to the 0 power, that's 1. So I have 0 minus 1/2 times 1 should give me negative 1/2. This is my y value. So y is equal to negative 1/2. At this point, I have everything I need. I have my x value, I have my y value, I have my slope. Let's write the equation of the tangent line. Let's do that in green here. So when we set this up, y minus my y value was negative 1/2, so y minus negative 1/2 equals m, that's my slope, so we said 3/2 times x minus my x-coordinate in this case was 0. I'll take this equation real quick and solve it for y. So first of all, I see minus a negative, that's really plus a positive, y plus 1/2 equals, here if I take 3/2 distributed, I have 3/2 x minus 0. So I should end up with y equals 3/2 x minus 1/2. Here is the equation of my tangent line. So really not too bad, I think, once we get the derivative. It's getting that derivative and particularly working with this term right here that can be really, really tricky. So I would be careful and I would practice some problems like that. a really common trick that I will throw in there is I'll say, well, go find the derivative. This is unrelated. But if I said, go find the derivative of, say, e to the 4th power. That kind of looks like a power rule, kind of looks like e to the x, but remember this is actually, if I look at e to the 4th, that's e times e times e times e, where e is a constant. It's a constant times a constant times a constant times a constant. This is a constant. Derivative of any constant is 0. So just keep an eye out for problems like that. I really like to throw those in from time to time just to kind of make sure that you're paying attention, make sure that you're not asleep at the wheel or anything like that. Part B, this one's, we're going to see this question an awful lot too. It says, find the points on the graph of f at which the tangent line is horizontal. So I have a few things that I want to think about here. First of all, whenever I see tangent line, hopefully when we think about tangent line, we're thinking about the derivative. Automatically, I want your mind to kind of wander to the derivative. So if we see the words tangent line or slope of the tangent line, I want you to automatically start thinking about the derivative. So okay, we're thinking about the derivative. What about the derivative? Well, I want the tangent line to be horizontal. What do I know about a horizontal line? If I were to sketch a horizontal line, so here's my coordinate axis, here's a horizontal line, what's the slope of this line? Well, slope of that line is 0. It's neither increasing nor decreasing. So this is really saying I want a tangent line whose slope is equal to 0. So in other words, I want to take my derivative and find the points that make the derivative equal to 0. So I essentially just have an equation to solve here. I'm going to take my derivative, set it equal to 0. And we actually found the derivative before. Let's go back and get it. We said 2 minus 1/2 e to the x. That was our derivative. So I'm going to take 2 minus 1/2 e to the x, set this equal to 0. I'm going to solve this equation. So I want to get x by itself. I'm going to add 1/2 e to the x to each side. So 2 equals 1/2 e to the x. I'd really like to get rid of that 1/2, so I'm going to multiply both sides by 2. So I should have, 4 equals e to the x. So remember here, if you're trying to solve an equation that involves e to the x, your last step, I need to kind of undo this exponential. I need to figure out how do I get x out of this exponent. And the inverse operation, we would say, is we would take the natural logarithm of both sides. I want to take the natural logarithm because that's what undoes that exponential e to the x. So on the right-hand side, e to the x and natural log of x, those two are inverse operations, similar in the same way that, say, addition and subtraction are, and that they'll kind of cancel each other out, and the only thing I'll be left with is x. On the left-hand side, natural log of 4, you could type that in your graphing calculator and get back an answer. I'm not too concerned with that, though. I actually just prefer to leave it as natural log of 4. It's a more exact answer. But if the problem asks you to round, then yeah, you'll want to pump that into your graphing calculator. The one thing I am unsure of, and we can answer this question right now, it says find the points on the graph, right? Points makes me think of both an x value and a y value. I'm not sure if my math lab is going to want you to find a y value, but we can do that real quick. It's not too hard. Once you identify that x value, once you find the x value, so at this particular x value, that's where I'm going to have a horizontal tangent line. I'm just going to take that x value to find the y value. We're plugging that back into our original function. We're plugging that back into 2x minus 1/2 e to the x. So let's do that real quick, just so that we have it in case it's needed. F of natural log of 4 equals 2 times natural log of 4 minus 1/2 e to the natural log of 4. 2 times natural log of 4, again, you could get a decimal approximation, or you could just leave it as 2 natural log of 4, minus, remember that natural log and the exponential e to the x are inverse operations. Those two are going to cancel each other out. I'll be left with 1/2 times 4. So I've got 2 natural log of 4 minus 2. We could factor that and do all sorts of silly stuff with it, but really that's my y value. So if I wanted an ordered pair, I would say my x value is natural log 4, comma, my y value is 2 natural log 4 minus 2. So it depends on what my MATLAB asks for. If it asks for and just an x value, then you just need to give natural log of 4. But if they want an ordered pair, then we will also need to find the y value as well. So let's look at one more example here in this video, just kind of continuing our practice with derivatives. I have a function here, f of x equals x cubed minus 27x plus 5. Part A says find an equation of the tangent line at a equals 2. So, okay, I want to find the equation of the tangent line. A equals 2. I actually prefer the notation at x equals 2. I think that's a little bit more clear. So I have an x value, I need a y value, I need a slope, just like I have every other time. It doesn't matter what order you find those things in, but if you kind of have almost like a routine for these types of problems, I would recommend that you sort of stick to that routine. So I've been finding the slope of the tangent line first, so I'm going to do that. If I want the slope of the tangent line, I need the derivative, so f prime of x. This is just a nice power rule to work with here. So let's see, I should have 3x squared minus 27 is my derivative. To find the slope of the tangent line, I'm going to take x equals 2, plug that into my derivative. So f prime of 2 is equal to 3 times 2 squared minus 27. Let's see, 3 times 4 minus 27. This is 12 minus 27, looks like negative 15. So this is my slope. So I have my slope, I have my x value, I still need my y value though. Well, if I want the y value, I'm going to take that x value and plug that back into the original function that was given to me, because that's what tells me the y value. So f of 2 is equal to 2 to the third power minus 27 times 2 plus 5. So here 2 to the third, I have 8 minus 27 times 2, 54 plus 5 here. So let's see if I can do some mental math. 8 plus 5, I'd have 13. Take away 54, I should have negative 41 as my y value. So this is my y value. So I have my x value, I have my y value, I have my slope. I should have everything I need. So let's write the equation of the tangent line over here. Y minus my y coordinate is negative 41, equals m, my slope is negative 15, times x minus my x coordinate is 2. We'll just take this equation, solve it for y real quick. So I really have y plus 41 equals negative 15x plus 30. Subtracting 41, I should have y equals negative 15x minus 11. Here is the equation of my tangent line. So I really want us to get used to doing these problems. I really like them because it forces you to understand the difference between the derivative, what does that tell you, and the original function, what does that tell you, because it tells you two different things, but they're both really important, and I need to understand the difference between those two things. Next up, in part B, it says find the points on the graph of f at which the tangent line is horizontal. Oops. Again, I see tangent line, I'm thinking about the derivative, f prime of x. I see horizontal, I'm thinking about a slope of 0. So the tangent line tells me the slope of the tangent line, which we just said is 0. So I'm taking my derivative, f prime of x, setting it equal to 0, and solving. So my derivative, we found that earlier. That was 3x squared minus 27. So 3x squared minus 27, that is equal to 0. And then you can solve this however you like. This looks like it'll factor very nicely, so I think I'm going to factor. 3 times x squared minus 9 is equal to 0. 3 times, this is a difference of 2 squares, so x plus 3 times x minus 3 equals 0. If we take each factor, set it equal to 0, we should have x equals negative 3 and x equals positive 3. If we need to know the y values, we would take those and plug those back into our original function back up here. So if I needed to know the y values, I would say f of negative 3 here is equal to, I already forgot the original function, negative 3 to the third minus 27 times negative 3 plus 5, and you would go and calculate whatever that is. Same thing for f of 3. F of 3, you would tell me that's 3 to the third minus 27 times 3 plus 5, and then we'd get back a y value. But if you only need the x values, again, this is all that I really need. Usually the x values, that's kind of the most important part. That's what I care about most, because that tells me where I have that horizontal tangent line, and that's the most important part to me, is where does it occur. The y value, not so important. The x value, that's what we really, really care about. Let's see, part C, the last part of this example. It says, for what values of x does the tangent line, or line tangent, excuse me, thinking about the derivative f prime of x, tangent to the graph of f have a slope of 21. So here they're telling me the slope of the tangent line is 21. So really similar example to the last one I just did. I'm essentially trying to solve the equation f prime of x equals 21. I want the derivative, which tells me the slope of the tangent line, to equal 21. So I'll take our derivative, which we said was 3x squared minus 27. Set that equal to 21, and then solve this equation. So let's see, what would be the best way to do this? I think I'm going to solve using square roots this time. I think that's probably a little bit easier. 3x squared, I'll add 27 to each side, so I should have 48. Dividing by 3, I should have x squared equals 16. Taking the square root of each side, I have x equals plus or minus 4. So that means at positive 4 and at negative 4, my tangent line has a slope of 21. Here are my solutions. So the derivative, finding the derivatives of these types of problems when we're working with just, say, polynomials, is not terribly difficult once we have the power rule. That really, really expedites the process. But I really want you to continue to practice this application of the derivative so that we know, okay, here's what the derivative tells us. It tells us the slope of the tangent line. Here's what the original function tells us. It tells us the y value. These two things are very, very different, but we need to keep them straight in our head. So I would highly recommend you practice a few of these examples.